Today we'll be talking about scanning. So in the previous lectures, we went through an overview of compilers, and we now know the main parts, the main components of a compiler, and we know what each one of them does. And today we will start learning how each of these components or parts or phases in the compiler does its work. So the first part of the compiler that we will start discussing is the scanner, how compilers do scanning. And compilers do scanning using finite automata and regular expressions. So we will start by reviewing the concepts of finite automata and regular expressions. So I will assume that you are already familiar with them, but we are just reviewing them, and we are emphasizing some of the important concepts that we need. So, and then we will explain how these are used in building a scanner. Okay. So in your theory of computation class, in your theory of computation, CSC 135, the class was about the notion of a language. So what's the definition of a language in theory of computation? What is a language? Okay, so regular expressions and automata, these are tools for recognizing languages. But what is a language?
Context-free grammar.
Well, a context-free grammar is another tool for recognizing another kind of languages. Yeah.
I'm not sure if I remember the definition exactly, but it's a finite set of symbols who the various combinations mean different things.
Well, in fact, symbols constitute the alphabet. So the alphabet is a bunch of symbols.
Right.
The alphabet is a finite set of symbols. Then the string, what's the string?
A series of characters from the alphabet.
Yeah, it's a sequence of symbols from the alphabet. So a string over an alphabet is a string, is a sequence, I'm using the word that I'm defining, which is a terrible thing to do. Sequence of symbols from the alphabet. So what's a language?
Isn't it the set of all strings with the
No.
grammar rules?
Okay. So concept-wise, so the grammar is just a tool for recognizing languages. So finite automata, regular expressions, grammars, these are tools for recognizing languages. A language is just a set of strings. It's just a set of strings. So this is what we call a formal language. So the language in your theory of computation class is what we call a formal language. To distinguish it from human languages, or natural languages, and to distinguish it from programming languages. So there is a relation between a programming language and a formal language that we will be understanding in this course. A formal language, the language that you studied in 135 in your theory of computation, is a general concept. So any set of strings is a language. Whether that set of strings is interesting or uninteresting, that doesn't matter. It doesn't have to be an interesting language. It doesn't have to be meaningful. It doesn't have to be useful. Any set of strings is a language. Okay. Now, in this course, we will be defining some languages that are useful. In particular, for a programming language, when we are building the scanner, we are basically defining the language of all possible tokens in that language, all legal tokens in the language. For example, x12 equals 32. Okay, so this is a string, and this string has these 4 different tokens. So we are looking for a mechanism for recognizing tokens that are legal tokens. So we will be defining some rules. We will be setting some rules to define the legal tokens in a programming language. So this token, this is an identifier. This is a variable name. This is the assignment operator. And this is a constant integer, unsigned integer. And this is the end of statement. Okay, so what we will be doing here is that we will be defining a rule for each of these parts of speech. And in fact, a string that has a number of valid tokens is a string that belongs to the language that is the union of all of these languages. So the language of all legal identifiers is a language, is a formal language. The language of all legal identifiers. The language of all legal unsigned integers is another language. The language of assignment operators is a language that has a single string in it, which is this operator. So this is a language that has only a single string in it. This is a language that has all legal identifiers in it, and a language that has all legal unsigned integers in it, and a language that has all legal end of statement characters in it, which is a language that has a single string in it. So this language has a single string in it, which is only this. And the language now, the union of these languages is going to give us the language that has all valid programs. All valid programs, at least at this level, at the scanning level. A valid program is a program at this point, from scanning point of view. We haven't gotten to parsing yet. From scanning point of view, a valid program is a program that consists of a sequence of valid tokens. And each token belongs to a valid part of speech. So the part of speech here is an identifier, and this is a valid identifier. Okay, so this will become clearer when we give specific rules, for recognizing these languages. But for now, let's continue our review of the concepts of formal languages and finite automata and regular expressions. So finite automata and regular expressions are tools for recognizing languages. And what does it mean? What does recognizing a language mean precisely? When we say a finite automaton recognizes a certain language, what does that mean precisely?
That it will accept the language as being valid.
It will not accept language, it will accept a string. So given a string, it tells you whether that string belongs to the language or not. This is what recognizing a language means. It means this tool, which is a finite automaton or a regular expression, takes a string and it tells you whether this string belongs to the language or not, whether it's a valid string for that particular language or not. Okay? So now the question is, what kind of languages are recognized by finite automata and regular expressions? what do we call the languages that are recognized, that can be recognized by finite automata and regular expressions?
Regular language.
Yeah, regular languages, exactly. So regular languages can be recognized using finite automata and regular expressions. Is there another tool that can recognize regular languages? So there is another tool that you have probably studied in 135 that can recognize regular languages, in addition to finite automata and regular expressions. Yeah.
The regular grammar?
Yeah, exactly, regular grammars. So you can also use regular grammars to recognize regular languages. Okay, so we will not say much about regular grammars here. We will focus on finite automata and regular expressions. So let's take an example of a regular language that can be recognized by a finite automaton. So the language is language L, which consists of the set of strings W, such that W contains 101 as a substring. So this is an example. Now we can build a finite automaton. We can build a regular expression, or we can write a regular expression for this. So let's first do a DFA for L. What is a DFA? Deterministic finite automaton. So we have a DFA, deterministic finite automaton, and NFA, non-deterministic finite automaton. Okay, so let's do a deterministic finite automaton. So for this, so we need to recognize a language that contains this as a substring. So obviously we have to have this substrings encoded somewhere in the automaton. Then we will decide what to do next. So this string must appear somewhere, substring, that we're trying to recognize. Now, okay, in a DFA, how would you define a DFA? And how does it differ from an NFA? Yes, please.
The deterministic finite state automata, every single path is mapped out no matter what. You don't, so even basically, sorry.
Okay.
In my mind. Every single path has to be mapped out. It can't be incomplete like a non-deterministic.
Okay, so if I have a state here, so these are what we call states, right? So what are the restrictions that I have when I'm building a DFA on a state? So what are the conditions that I have to satisfy in order for my finite automaton to be a deterministic finite automaton? Yes?
One in, one out.
Well, I have to have one edge for every
possible state that it can be in.
No, not for every possible state.
Well,
I have to have one edge for every?
input possibility.
No.
Every symbol in the alphabet.
For every?
In a symbol in the alphabet.
Exactly. For every symbol in the alphabet. So I have to have one transition, one edge for every symbol in the alphabet. So if my alphabet here, by the way, in theory of computation, we tend to use sigma equals 0, 1 as our default alphabet. This is the simplest alphabet that we can use for explaining ideas. So for every symbol in the alphabet, you have to have a transition. And you have to have exactly one transition for every symbol. So this is a DFA. While if you have something like this, you have two transitions for a 1, then this is not a DFA. This is an NFA. If you have this, if you have a transition for a 1 and you don't have a transition for a 0, then this is not a DFA, this is an NFA. And what else can you do in an NFA and cannot do in a DFA? What else? What is that important thing that you can do in an NFA but cannot do in the yes, Eric?
Backtrack.
No. In terms of defining transitions, yeah.
Oh, the lambda symbol.
Yeah, okay. The empty string, yeah, the epsilon, the empty string, whether you call it lambda or epsilon, we will call it epsilon here. So if you have something like this, an epsilon transition, then this is not a DFA, this is an NFA. Okay. So when you are building a DFA, you have more restrictions. So the DFA is more restricted. You have to have exactly one transition for every state. Out of every state, you have to have exactly one transition for every symbol in the alphabet. If you have multiple transitions for one symbol, that's an NFA. If you have symbols that do not have transitions at all, then that's an NFA. And if you use the epsilon, the empty string transition, that's not a DFA, that's an NFA. Okay. Now, which one is easier to work with?
NFA.
Yeah, the NFA is easier because there are less restrictions. You don't have the restrictions. You can do, you have more flexibility. So in this case, let's do a DFA. Now we are more restricted, so we have to figure out the actual a transition for every state, a transition for every symbol. So what we have on the board now is not a DFA. It's not defining what to do for every symbol in the alphabet. So now we need to determine here what will happen if we have a 0. We just stay. We're not making progress towards the goal. The goal here is to get 1, 0, 1. So if we're getting a 0, we're not making progress. So now this Q0 is done. We have defined all possible transitions for all the symbols. For Q1, we're saying, OK, if we get a 0 and we are here, then we are making further progress. But what if we get a 1?
Stay there.
Go back to Q0? Yeah, we stay here because we already have the 1. Right? So if we get a 1, then we are staying here because now the last one that we got, the last one that we have read, becomes the first symbol in the substring that we are trying to recognize. Okay? So now we have defined all transitions for Q0 and Q1. Now for Q2, if I get a 1, then that's what I'm looking for. If I get a 1 when I'm here, I get a 1 and I have already seen a 1 and a 0. So I have seen the substring that I'm looking for. If I get a 0, I have to start over, right? If I get a 0 here, it's just like getting 1, 0, 0. Then I will have to start over because I'm looking for 1, 0, 1. So if I get a 0, start over. Now I need a 1 in order to start recognizing that substring that I'm looking for. OK, is this complete?
No.
No, it's not complete. What else do we need?
Final state.
Oh, the final state. Where is our final state here?
Right.
Yeah, the last one. So this is the final state. We distinguish this with a double circle. So this is what we call a final state or an accept state. Final state or accept state. What else is missing? Yes?
When you're in the final state, you can still accept more zeros and ones.
Yeah. So when I'm in the final state, when I'm here, I've already seen the substring that I'm looking for. So after that point, whatever I get, this string is satisfying the condition of the language. This string, I know that this string already belongs to the language. So no matter what I get here, I will stay in the final state. The string has already satisfied the requirement to be a member of this language that I'm trying to recognize. Okay, so this is a DFA. Now, let's do an NFA for language L. Now, if I'm asking you this question in the exam and I'm asking for an NFA for this language, will this be a correct answer?
Yeah.
Yes, it will. Because the DFA is an NFA. You know, the DFA is the one that is more restricted. So every DFA is an NFA. It's easier to be an NFA. To be a DFA is harder because there are more restrictions, but not every, the opposite is not true, but not every NFA is a DFA. The opposite is not true. But let's now write an NFA taking advantage of the the convenience and the flexibility of the NFA. We don't have to think about everything. You know, for an NFA, we can just say, okay, in order to have this substring, all what I need is 1, 0, 1, and this is my accept state, and what else? What do I need to add in order to make this a valid NFA for this language? So this is the string that I'm looking for, but what will be before it or after it?
Empty.
Empty? No, not empty. I'm looking for a string that has this as a substring. So before this string or after it, what can I have? Anything I want. So how do I express this anything? How do I say anything? Using the NFA.
Like a star or something.
Okay, that's a regular expression. So here, so I just loop here. So you can say whatever I get here, I can loop, and I can loop here. So a loop, a loop in a finite automaton corresponds to a star in a regular expression. So starring is repeating or looping. So what I'm saying here is that, okay, I'm looking for a string that has 101 as a substring, and before it I can have anything. After it, I can have anything. So this makes an NFA easier to write than a DFA. Why is it easier? Because we didn't have to explicitly cover all the transitions. So for example, from Q0, we have two possible transitions for a 1. So if we are in Q0 and we get a 1, there are two possibilities. We either stay in Q0 or go to Q1. And this is the non-determinism. This is what makes it non-deterministic. It is non-deterministic in the sense that when I'm here and I got a 1, I have two possibilities. In the DFA, there is exactly one possibility. When you are in a given state and you get a certain symbol, then there is always one possibility. Here, you have multiple possibilities, and sometimes you don't have. So if you are in Q1 and you get a 1, what does this mean? So we're not explicitly saying what will happen if you are in Q1 and you get a 1.
Q0. Back up to Q0.
Well, we're not saying go back here. So when we are not explicitly giving a transition in an NFA, what does this mean? What does it correspond to in a DFA? Yeah.
Infinite. It goes into the, I guess, trash state where it loops back into itself constantly.
Yeah, it goes into a trap state. It's like, we are dead. It's a dead path. But the good thing about the NFA is that there are multiple paths. Okay, so there are multiple paths. So the NFA is a compact way of representing multiple paths in a more compact way. Usually the NFA is more compact than the DFA. It's not clear in this example, but it's more compact because it's encoding multiple paths and multiple possibilities. So it's telling you here, Q0, when you're in Q0 and you're getting a 1, you can go here, but you can stay here. Both possibilities are there. So which possibility should I do? All possibilities. So in order to determine if a given string belongs to a language or not, you have to find at least one path that leads from a start state to an accept state. If you can find one path, then it's accept. If you cannot find any path, then it's reject. And there are many paths. Okay. In fact, this will become clearer when we look at the conversion from an NFA to a DFA. So in 135, you have seen an algorithm or a procedure for converting an NFA to a DFA or a DFA to an NFA. An NFA to a DFA. A DFA does not need to be converted to an NFA because it's already an NFA. But an NFA is not necessarily a DFA. So there is a procedure for converting an NFA to a DFA. And what's the name of that procedure? Okay. So it should be, the name of the procedure has to do with the way it works. It's the subset construction. It's called the subset construction. We will cover the subset construction in detail in one of the next lectures. So today we're only trying to cover the basic concepts of NFAs and DFAs. Okay, so now the power of the NFAs, we can see it in an example like this. If L is W such that W contains the substring 101 or the substring 111. Okay, so this is something that we can do easily with an NFA, but with a DFA we'll have to think more. So this can be much more easily done using an NFA. So whenever we have an OR, what's the standard procedure for building an NFA for this OR?
Is it a branch?
Yeah, exactly. So we just have a start state, and then we have two possibilities. One is for the first language. So this OR corresponds to what language operation, what set operation. Because a language is a set of strings. So the OR here corresponds to what string, set operation, the union. Yes. So this is a union. Okay, and this is 1, and then before and after I can put anything. Okay, so just, and again, one little exercise to refresh your memory. What if we change it to contains the substring 101 or ends with the substring 111?
On the substring 111, get rid of the loop on the final state.
Exactly. So all what we need to do is to get rid of this. Now we're saying that the string must end in 111. Okay, so with this change in the language in red, we have this NFA. So we no longer need the last loop. Yes?
Shouldn't we also put on the top one a epsilon leading to the bottom one, since you can have the top one and the bottom one at the same time, technically?
What do you mean? Here?
Yeah.
In the final state? Okay, so are you suggesting that we have one unified final state? Is that?
No, just have the top one lead to the first one of the bottom one, because you could go through the top one, loop, and then end in 101, right?
Okay, but you have two possible paths, right? You have to be careful about the NFA because it has a large number, potentially a large number of paths hidden in it. So it's a compact encoding for a large number of paths. So here, no, we don't need to link these at all. So in order for a string to belong to the language, you have to find one path that leads from start to accept. And we have two accept states. So in other words, give me a string that cannot be recognized by this NFA. A string that belongs to the language and cannot be recognized by this NFA. Can you give me a string that belongs to the language and cannot be recognized by this?
Not off the top of my head, no.
Okay, because there aren't any. Because this is, this covers all the strings. Because in order for a string to belong to a language, it has to either have this or this. And a string can have both, right? So, a string like this, for example, 1 1 0 1 1 1. So this satisfies both conditions. But in order for this string to be recognized by the NFA, you only need to take one path. So you are playing the advocate of this string, trying to just find one path. All what you need to do is to find one path that will make it qualify as a member of this language. So in this case, you have two options. So for example, this is 101. So okay, you have the option of you take this and you stay here for the first one. For the second one, you advance here. Then with the 0, you advance here. With the 1, you advance here. And then you stay here. So for these two ones, for the last two ones, you are here. Another path that you can take is this path. So in this path, how many times do you stay here for the first
three?
For the first three. So for this, and this, for these first three symbols, you choose to stay here. And then towards the end, when you have three remaining, you take this path and you advance to the accept state. So the NFA is easy to write, but in fact, tracing it is harder than tracing the DFA. The DFA is deterministic. And this leads to a very important question, which is a question that is extremely important here. Which one is more easily programmable? If you were to write a program to implement this or this, which one will be easier to implement as a program? DFA. And this is exactly why in our scanning, eventually we will build a DFA, because the DFA is almost ready for programming. It's just a table that tells you where to go. So if you look at what we call the transition table for this, the transition table for this is Q0, Q1, Q2, Q3. And if you are in Q0 and you get a 0, then you go to Q0. If you get a 1, then you go to Q1. If you are in Q1 and you get a 1, you stay in Q1. If you get a 0, you go to Q2, and so forth. So this is the transition table for the DFA. While the transition table for the corresponding NFA for the NFA, and we are referring to this NFA. The NFA for the same language. So here we have 0, 1, Q0, Q1, Q2, Q3. Now, if we are in Q0 and we get a 0, where do we go?
Q0.
To Q0. And if we are in Q0 and we get a 1, where do we go?
Q1.
0 or 1. How do we express this? We express it as a set of states. So in the DFA, in the NFA, you go to a set of states. So this is, you go to Q0 or Q1. This is the set of states that you can go to. So while this, in fact, this should be a set as well. So in an NFA, given a state and a symbol, you go, in general, you will go to a set of states. That set of states can have many states in it, and it can be empty, and can have one state in it. But in the DFA, you go to exactly one state. And this is just ready to be programmed, because all what you need to implement this thing is a switch statement. So it's, you can just so you can do something like this. Switch of state. And if you are in Q0, if the symbol or if symbol equals 0, go to state Q0. If symbol is 1, go to Q1. So you know exactly where to go. So you can implement a DFA easily as a switch statement because it's deterministic and you know exactly where to go. But NFAs are easier to write. And in fact, what's easier than an NFA is a regular expression. And a regular expression is an even easier way of expressing a rule about languages. So let's now look at regular expressions. Now, regular expressions can be easily converted into NFAs or DFAs. So in 135, you studied a way of converting regular expressions into NFAs or DFAs. DFAs? So can a regular expression have epsilons? Can a regular expression have epsilons in it? Empty strings? Yes, it can. So if it can have epsilons, then it can be easily converted into an NFA. Right? So it can be converted into an NFA. So converting a regular expression. So what's the name of the procedure for converting an NFA to a regular expression? Does anyone remember? So that's the Thompson construction. Okay, so the Thompson construction is an algorithm for converting an NFA to a regular expression. Now, what's a regular expression? How would you define a regular expression? So what can you have in a regular expression? What are the main elements in a regular expression? So for example, okay, let's take the same example. L contains 101 as a substring. How would you express this as a regular? How would you write a regular expression for this? Yeah.
Parentheses 0 or 1, unparentheses star, then 1, 0. 1.
Okay, so you're saying 0 or 1 star?
Yes. And then...
By the way, I prefer to use the union here because you can use the union or you can use the OR operator. But if you use the OR operator, make sure that you make it longer than the 1. But I prefer to use the union. Okay, you can use both. So 0 or 1 star.
1, 0, 1 for the substring.
1, 0, 1.
And then 0 union 1 star.
0 union 1 star. So there is a shorthand for 0 union 1. So 0 union 1 can be written as what?
Star.
Star? Sigma, the alphabet. So it's the set of all possible symbols. So that's sigma. So this is equivalent to sigma star 101 sigma star. Because sigma and 0 union 1 are the same thing. Sigma is the alphabet, the set of all possible symbols, and 0 union 1 is 0 union 1 is sigma. So this is a regular expression. So in fact, what happens in scanning, scanners and compilers are built by writing regular expressions for the different parts of, for the valid tokens in a language, like identifiers, integers, floating point, if statements, whatever. Every valid token, there is a rule that defines it using regular expressions. Then we take this regular expression, big regular expression that we build for the low-level syntax of the language, or the micro syntax, the syntax at the word level. We take it and we build an NFA using the Thompson construction. Then we take that NFA and convert it into a DFA using the subset construction. So we start with a regular expression because the regular expression is the easiest way for humans to define the rules for a regular language. It's the most convenient way, hopefully, for most people. Regular expressions are easy to write, relatively easy to write. But we end up with a DFA. Why? Why do we, at the end, convert this into a DFA? Because we can code it. So a regular expression, trying to write a program that implements a regular expression. What does it mean to write a program that implements a regular expression? A program that takes a string, the input is a string, and the output is yes or no. The output is accept or reject. So writing a program that takes a string and tells you whether this should be accepted or rejected. If you think about it, if you think of building a program for a general regular expression, you'll see it's very hard. But if you think of writing a program that implements a DFA, it's very straightforward. Like we said, you can just implement it as a switch statement. So that's why we want to end up with a DFA. Okay, so should we take more regular expression examples? Because in fact, the tool that we will be using, which is Flex for building scanners, so we will be using a tool that will generate a scanner for us. So what we feed into this tool is a file that has regular expressions in it, and the tool does the job of converting the regular expression into an NFA and then converting the NFA into a DFA. So that conversion is done automatically by the tool that we will be using. So you give it a regular expression, and in fact, it gives you C code. So it converts it into an NFA, then it converts it into a DFA, then it generates code for the DFA, which is straightforward, and it gives you the C code. So, but even though the conversion from NFA to DFA and from regular expression to NFA, even though that's done by the tool, this doesn't mean that we shouldn't understand it. So we need to understand this, even though it's not even though it's automated and it's done by the tool. We need to understand how it's done. And in fact, this is covered in a standard. This is usually covered in a standard theory of computation class. Conversion from an NFA to a DFA and conversion from a regular expression to an NFA. Let's take some more examples. A couple more examples. For example, L equals the set of strings W such that W has an even length. So the set of strings that have an even length. So how would you? Yeah.
Either WW star or sigma twice star.
Sigma twice. Yeah. So you have to have two sigmas. Star.
Yeah.
So start means repeat this as many times as you want. Right? So you can. So this is a string that has an even.
Star is 0 or more, I believe. So 0 is considered an even number.
Yeah. So 0 is considered an even number.
Yeah.
Right?
So
So how about odd? Okay, W has an odd length. So to make
it'd be that with another sigma after the star.
after or before?
After, or it doesn't really matter.
Doesn't matter. Yeah, that's the answer. It doesn't matter. You can put it before or after. Okay. You can put it before or after. So it's a string. If it has an odd length, then you have to have at least one symbol, and after that you'll have an even length string. Right? Yeah, and a string that has 0 symbols in it, a string with 0 symbols is considered an even length string. So 0 is considered an even number here.